So this is question number 41 of GATE 2022 Metallurgical Engineering. So we have to match the column from 1 to 2. In column 1 some term is given, and in column 2 explanation of that particular term is mentioned, and we have to match them basically. The concept related to this column, if you want to understand in more detail, you can refer the lecture which I have mentioned in the reference section. So now let us go one by one from the column 1, and then we will finally match the right explanation in column 2. So the first term is mentioned here is Cartilage Atmosphere. So when this type of atmosphere is created, we'll understand that. So in a material like low carbon steel, where we have iron and carbon as an alloying element, so this carbon is basically present in interstitial places. So what happens is, in order to minimize the system energy, this carbon atom will diffuse and it will reach to the dislocation line, like it will diffuse along the dislocation line. So you can see here we have a matrix of iron. Here this carbon got diffused, right? Interstitial carbon atom is diffused along the dislocation line, and this is our basically extra half plane of that particular edge dislocation. So what is the effect of this diffusion of carbon atom to the dislocation line? When you apply stress, and if that stress is good enough to cause a plastic deformation in your material, so the yielding will happen, and that yielding will have two values, like one will be having upper yield point value, which will be the highest yield stress value, and then after that this yielding will occur at constant stress, and then again the value of stress will be increasing as you want to deform the material more. I have a graph, load versus elongation, and you can see here this is our elastic strain which we have generated inside the material, and this is the upper yield point, and this is the lower yield point value. So what is happening is, in order to break the bond between this interstitial carbon atom and this extra half plane of iron atom, we have to apply a very high stress, which is correspond to upper yield point, and after that along this line the bonds between this carbon atom and this iron atom will be breaking. During this constant load region, what will happen, which is called yield elongation, and here bands will be appearing on your sample, right? And this band will be basically inclined to the 45 degree. If you are applying load in this direction, so this will be making a 45-degree angle with your applied stress or load direction, right? And these bands are basically known as Luder bands, right? So if you see in the problem, the Cartilage atmosphere basically is related to Luder bands. So the right option for P will be third, which is Luder bands, right? Now coming to the next option in column 2, which is Suzuki Interaction. So what is Suzuki Interaction? So basically if you write Suzuki Interaction, so what are they basically? So it is characterized by the segregation of solutes to the stacking faults, right? So basically here what is happening, our solute atom is getting segregated in the stacking faults. So for example, when the dislocation in an FCC system splits into two partials, then in that case what will happen? A HCP stacking fault will be created, right? Formed. And between these two partials, which is leading to the creation of stacking fault, this solute atom will be segregating, and this interaction is known as Suzuki interaction. So Suzuki interaction is nothing but segregation of solutes to the stacking faults. So for Q4, option 4 will be the correct match in the column 2. Now so in the Boschanger effect, what will happen? Let's say if a specimen is deformed plastically beyond the yield stress in one direction. So you are deforming your sample plastically in one direction. So first the elastic strain will be appearing, then plastic yielding will take place. So at this point your material, let's say, is yielding. So let's say denoted by sigma A, which is the yield point. So this is our plus, which is basically tension, and this is minus, which is compression. So if you are applying and deforming your material in one direction, and after that loading you are making the applied stress to 0, and then again you are reloading it in reverse direction, then what will happen? Then after the elastic strain, the plastic strain will be occurring, and this yielding in the reverse direction, let's say is denoted by sigma B, will be occurring with the lower magnitude of stress as compared to the yield stress in the earlier one. So basically what I am saying is the magnitude of sigma A will be greater than the magnitude of sigma B, right? So in the reversal case, the yield stress will be lower than in the earlier case. So why this phenomena is happening is due to when you are applying a tensile load that is in this direction. So what will happen? Dislocation will be moving, and it will be piling up at some barriers, and this pile up of dislocation create a back stress in opposite direction. Now once you drop to the 0 applied stress value and reloading it in the reverse direction, this back stress will be basically in the direction of compression, which is reverse direction of tension here, this direction, and this will aid the dislocation movement when the direction of slip is reversed. So in that case the yielding will be occurring at a lower stress than the yielding in the earlier case, right? So this is the reason, and this phenomena of decreasing yielding stress when the loading direction is reversed is known as Boschanger effect. So Boschanger effect is basically what? Decrease in yield stress when loading direction is reversed, right? So for option R, option 1 in the column 2 will be the correct match. For P it was loader band, Q it is option 4, and R it is option 1. And for last option, which is Nabarro herring creep, basically it is controlled by stress directed atomic diffusion. Stress directed atomic diffusion. In this type of creep, diffusion of vacancies through lattice will be taking place. and that will be causing plastic deformation in that particular polycrystalline material. And this type of Nabarro herring creep, basically they occur at a very high temperature, and relatively low stresses, like sigma upon g value will be less than 10 to the power minus 4, and homologous temperature, if you see homologous temperature, it will be equal to 0.8. So the Nabarro herring creep is basically stress assisted diffusion of vacancies resulting in plastic deformation in a polycrystalline material. So the right option for S will be 2. So if you see the options, for P it is 3, P3, Q it is 4, Q4, R it is 1, and S it is 2. So the option C is the correct match of column 1 to the column 2. Thank you.